Hello everyone, this is Noah, working with Math 302. So this one was kind of a fire hose, and so hopefully I understand this correctly. If I do anything wrong, please comment. Okay, 3.5. We got to put that 3.5 in linear algebra. All this is saying, so we learned about subspaces, basis, dimensions, and rank. All this kind of is just relationships between matrices. We're not really like learning any like how to solve this. These are just relationships and theorems between matrices and spaces within them. So, for example, let's start with a subspace. A subspace is just a span. My handwriting's horrible, but it's just a span. So a span is something that contains all linear combinations in that span. And so a subspace is just a span. And within a subspace, there's a basis. And within the basis, there's the dimension. Okay, so they're like inside each other. So you think, okay, you go from span to subspace, because a subspace is like a space within that span. And then a basis is a simpler form, in fact, the most efficient form of that subspace slash span. And a dimension is really like a description of that basis. So, continuing on, we're going to try and see how to find the basis from subspaces. So we have three subspaces in the matrix. Specifically, there's three. There's the row space, there's the column space, and the null space. So how you find the row space is first you find the reduced echelon form, and then you use the non-zero rows, row vectors, really to form the basis for the row space. So if you had 1, 0, 0, and let's see if I can come up with a good example. In this row, you can't see, and then a 1 there, we see that these bases are not dependent on each other, linearly dependent on each other. And so you would write this as the basis for this row is 1, 0, 0 and 0, 1, 0. Something that wouldn't be a basis was if I added a 2, 2, 0 on here. And we see that this can be a multiple of that, and that can be a multiple of that. Or more like, I'm going to put 0 there. Yeah, that's easier. So this is just a multiple of that, and so it's dependent. So not independent. So that wouldn't be counted. That wouldn't change anything. So you want to look for, these are things that are dependent on each other. They're yeah, I'm butchering this. Hold on. Let me find what the example gave. Okay. So the basis for the row space is, so you do put it in reduced row echelon form, but then you just take the non-zero rows, basically what you do, and that's the basis. So these non-zero rows, but also that aren't multiples of each other. So then in the column space, is you also find the reduced echelon form, and this one you're just going to use the pivot columns. So for example, in where is is it? So in the book, find the basis of the column space of the matrix. They reduced it, and then they had it to here. And then what they did was they found the pivots. So there's a pivot here, and a pivot here. And the ones that have these pivots are the ones that are the columns that they're going to use in the original matrix. So since there's a pivot here, this column is independent. Pivot here, this column is independent. Pivot here, this column is independent, the fourth column. So you reduce it, and then the columns with pivots in it are the ones that are the basis for the column space. To find the basis for the null space is you find the reduced echelon form, and then you solve using the free variables from the AX equals 0. So for example, okay, so what you want to do is, here we have a reduced matrix into row echelon form. So once you get the matrix down to row echelon form, first you're going to augment it to put on the equals 0, because technically the matrix times 0 is equal to 0. And so this is just, so we want that to equal 0. I'll leave it at that. So there's some x multiplied into those that are going to equal 0. So this is like just finding a linear combination. And so you just solve for that. And so here we have a free variable there, and I guess a free variable there. And so we see that we have two free variables. And you solve just like it was a linear combination. And you can pull out the S and T's there. So let me try and explain this better. Solve the augmented matrix. Find the solutions with whichever variable you decide, whether you put it in parametric or leave it in x1, x2, x3, x4, and so on and so forth. And then divide it out. And these are just vectors. Technically, this is just a vector times s and a vector times t. Okay, so that's how you find the basis for the null. How to find the subspace, how to find something in the subspace now. So, for example, if the question, so these are the subspaces again. So now the question is this in the row subspace, the row space? Is this in the column space? Questions like that. These are kind of easier. So for row A, you're going to set up an augmented matrix. So you're going to have, number, here, number. And the thing that they're asking, the vector that they're asking if it's in the row space is here. And so if there's a solution to this, then it is in row space. So, I wrote that down up there by null, but that applies to down here. Okay. The column space is you use a vertical augmented matrix. So it looks kind of like this. So I have number. And then what I'm going to do is I'm going to put kind of like an augmented thing here. It's not really like this. I'm just kind of calling it that. And then number. You put down an extra row. And then you try and make these zeros. If they can't be made into zeros, then it's not in the column space. But if these do become zeros, then this vector is in the column space. And then something in the null space, the null is defined by AX equals 0, so A matrix, and then this is a vector, and it equals 0. So what you do is if they give you a vector and they say, is this vector in the null space, you just plug it in right there, and you need to get 0. So that one's definitely the easiest. Okay, final word on dimension and rank. So dimension, like I said, was just a description of the basis. So a dimension is just the number of vectors or elements in that basis. And then rank is a type of dimension where it's the dimension of the column space. In other words, rank is your number of pivots, and nullity is your dimension of the null space, or nullity is your free variables. Free variables. Rank plus nullity is equal to the number of columns. So you can find either one of these using this theorem here. So rank is the pivots, nullity is the free variables, and then the number of columns is equal to nullity plus rank. And those are all dimensions there. And these are the number of elements. Okay, hopefully that made more sense. Okay, thanks for watching.